My name is Sadia Anwar and I am the commissioning editor at River Publishers. Today we have a special guest, Professor Porath from the Hebrew University of Israel, who is an expert in biomedical engineering and molecular electronics. We are currently at the Conference of Self-Assembly and Molecular Electronics at Aalborg University, Denmark, where we have found many interesting experts in the field, especially from biomedical engineering. And our guest is one of them. Despite their busy schedule at the conference, Professor Porath has kindly found some time to discuss the fascinating field of molecular electronics with DNA for nucleic acid detection. A big thank you to the conference team and organizers, especially Peter and Leonid, for making this happen. So let's start with the first question. Can you please introduce yourself and briefly describe your background in biomedical engineering?
Well, my background is actually physics, mathematics, and electronics. I studied at the Hebrew University in Jerusalem, and then continued for master and PhD in physics with Oded Milo on scanning tunneling microscopy. And later on, I continued to do a postdoc at Delft University in the Netherlands with Professor Kees Dekker. In fact, I was supposed to work on other molecules, and towards the end of my PhD, I heard a lecture by Erz Braun and Uri Sivan. Professor Uri Sivan is now the president of the Technion. At that time, they put a 10 micron long DNA molecule between metal electrodes, and then they covered it with metal to make it conductive. At that point, I asked them why they don't use the DNA itself, and they showed a graph that probably is responsible for over 2,000 citations for that paper, which was the pioneering measurement on a single double-stranded DNA molecule, and they showed that it's not conductive. I thought that a shorter molecule without defects and more stiff would be more suitable for such measurements, and I called at the same evening to my future postdoc supervisor, to Kees Dekker, and suggested to measure DNA. He told me that he heard about another team in Basel by Fink and Schonenberger who are already measuring DNA as well, and therefore a few months later, when I started my postdoc, we decided together that I will do measurements on single DNA molecules, and that's how I entered into this field. At that time, there was urgent need and a fear in the microelectronics industry that it will not be possible to continue the miniaturization, which is so important, which is the one that leading the huge computers of the past into very powerful computers in our cell phones, and because of limiting in the lithography, in the way to construct the wires. And the hope was that molecules, such as DNA, due to its double-strand recognition, will be able to replace and make electronic circuits that will be much simpler, much smaller, cheaper, and so on and so forth. So that's how I entered into this field. And over the following years, it came out that it is not so simple to measure DNA. That when we say DNA, it's a very generic term, and in fact, when you look at different DNA molecules with different length, with different sequence, with different other characteristic, you find that they are different, and that led to results that were seemingly contradictory. In fact, they were simply different. In addition, there was another important difficulty, which is measuring a single molecule. When we make optical measurements, we measure 10 to the infinity molecules. And when you go down not to a billion, not to a million, not to 100, not even 10, or two, and you just want to measure just one, you find that they are really different, and that where the power of measuring many single individual molecules come out and gives us the ability to address the individual properties of these molecules. So that's how I entered into this field, and later on I returned to the Hebrew University and founded my bioelectronics group. And we continued together with Professor Sasha Kotliar from Tel Aviv University, who is also in this conference. It's a 20 years long collaboration. He synthesizes molecules and we measure them. And we wanted to make better molecules, better conductors. So we chose several ways. For example, a four-stranded DNA, what we call G4 DNA, metallized DNA with gold particles or with ions that are inserted, and so on and so forth. Those can be found in our paper. However, at the same time, in parallel, the microelectronics industry progressed a lot, found ways to continue the miniaturization in excellent ways. So it seems that electronic circuits from DNA are not going to happen. However, there were two big challenges. One of them was the scientific challenge, to understand the charge transport in DNA. And the other is what can we do with this knowledge? So to address the first, with a long work of many years, ended with work of Dr. Roman Juravel, my student, who's now doing a postdoc. And we were able to measure DNA, for sure a single DNA, double-stranded DNA molecule. We were able to see that the molecule is there and measure it again and again. This was an important characteristic to make what we call a good experiment. And that way, this was published in Nature Nanotechnology about 2 years ago. And addressing the other challenge, it seems that now there are several methods to address sensing. For example, the recent pandemic exposed the need to identify and measure RNA very quickly and very sensitively and in a cheap manner. Cancer, for example, is another one where the expectation, I mean, there are many people who die from cancer. The expected cost of this cancer in the coming 30 years is about $25 trillion. And there is an estimation that by early detection, about a quarter of these deaths could be avoided. And so the detection of nucleic acids became central and is now the next goal, I think, of the field. So DNA in general and other molecules were the basis for molecular electronics that is changing its forms over the years.
It's quite impressive to know about your journey, and I can see that you can use DNA to multiple different ways.
Thank you.
Your work in this field is truly impressive. Collaboration is often crucial in research. What is the impact of academia-industry collaboration on the development of DNA-based molecular electronics?
Well, these works were done in collaborations. The primary one was the one I mentioned with Sasha Kotliar, but we promoted this activity through European projects. The first one was with 9 different groups on DNA-based nanowires. The goal was to develop wires based on DNA that are more conductive. For example, the G4 DNA, whose conductivity reported in 2014 also in Nature Nanotechnology. So there were groups from Israel, from Spain, from Italy, from Germany, and from Leonid, the organizer of this conference, from Denmark. And we were able to promote DNA-based nanowires. The next goal was DNA-based devices in another EU project, also with groups from Switzerland. And there we wanted to make a device based on DNA, which the dimer I described before was the end of and goal of this project, among others. And nowadays there is a change that is happening in academy over the last 20 years. There is an understanding that we shift from pure science to science that is supposed to give back the huge funding that is needed to do research as profit or a promotion or a benefit to industry. So now we promote entrepreneurship centers, for example, in our university. We collaborate with companies in order to do the sensing and so on. So the collaboration between academy and industry is growing. Nowadays, for example, patents are considered as another parameter for the promotion of scientists in the university and founding of companies, unlike in the past. So this collaboration is a needed and happening progress.
That's quite interesting. As we wrap up our small discussion, what advice would you give to aspiring researchers or students interested in entering the field of molecular electronics with DNA?
I would say that the mental strength is probably the most important, and endurance are the most important ones. To know and understand that when you do measurements, you get all kinds of results. Some of them may seem negative, but in fact they are the ones who give us the information in which direction not to go and in which direction later we should go.
Exactly.
And we should just make a plan. So the first thing is to set up an important goal far away. What would be the title of your nature, maybe, and then derive back what are the major steps that are needed in order to get that goal, and then do a careful planning of the first phase of this journey, and make a kind of a flow diagram. You check possibilities. Some of them are pointing to the right, some of them to the left, instead of saying yes or no. And then continue until you get that goal, and always do it with open eyes. For example, if there are new opportunities, things that you didn't think before, didn't expect before, that may lead to important unexpected discoveries, like many of the discoveries in science ever.
Lastly, what are your thoughts on the future of molecular electronics with DNA, and where do you see the field headed in the next 5 to 10 years?
Well, I think that the shift is from thoughts about electronic circuits that were like 20 years ago to sensing of nucleic acids, mostly in the biological, medical context. I think that's the future of this DNA-based electronics field.
Thank you once again, Professor Porath, for your valuable insights and for taking the time to join us during the conference at Aalborg University, Denmark. Special thanks to Peter and Leonid and the entire conference team for making this River Publishers podcast possible. We wish you continued success in your research and look forward to seeing the impact of your work in the future. Subscribe to the River Publishers podcast for more exciting episodes, and subscribe to our YouTube channel for more informative content. Until next time.